All right, here we are back again for the B lecture of week 4. We are going to continue our discussion on bias and assumptions. Basically continuing where we left off in the A lecture, because I reduced the A lecture in length a little bit. So because this is a bit of a shorter week than normally because of Carnival. So you can get a bit of a shorter lecture and before you can get to work on the assignment. So I'm going to pick up where I left off in the A lecture. So also I'm not going to start with the normal recap of where we are, and we're just going to continue straight on. So we're going to discuss bias and assumptions further. We're going to specifically also discuss the role of outliers in potentially biasing your findings and how you can find these outliers. And then we'll reflect a little bit on where are we now, what do we now know about regression analysis and how it works, how to interpret it, and what assumptions we need to make for regression analysis to give us unbiased estimates. And then we'll go a bit further and delving more into the issue of causality, and reflect a bit further on what does it mean to assume that our regression estimates can be interpreted as causal effects, and specifically what assumptions does that lean on, and how might those assumptions not be true, so what might violate those assumptions. So let's get straight into this. So I left off in the A lecture discussing the 4 standard assumptions of linearity and additivity, independently distributed errors. That's what I already discussed, and then there are 2 other standard assumptions that I did not yet discuss, homoscedasticity and normally distributed errors. So let's take a look at what that means. So when we talk about homoscedasticity, great word, but basically it's just a fancy word meaning the same variance. Yeah, homo for same, and scedasticity standing for variation of variance. So in other words, what is the assumption of homoscedasticity? It is the assumption that the variance of our errors is constant over the values of our x variables. So that if you think about the variation of the errors around our regression prediction, so think back to these pictures of how spread out are the individual data points around our regression line, then that variation should be roughly constant no matter where we are on the x-axis, so no matter where we are looking for with our independent variable. So in other words, basically the assumption that no matter what the value of our x variables are, our predictions are always more or less equally good. Yeah, that we are always more or less equally able to predict the dependent variable, and that's not a situation where on certain ranges of our x variables, our model does a better job at predicting the dependent variable than in other ranges. Yeah, so that is the assumption of homoscedasticity. And if that assumption isn't true, we call it a situation of heteroscedasticity. Yeah, hetero standing for different, and scedasticity still standing for just variation or variance. Yeah, so we assume that we have to assume that the errors that we observe are homoscedastically distributed, so constantly distributed. And if they are not, if there is some kind of pattern in the distribution of our errors, then we talk about heteroscedasticity. I think, for instance, of a model where, let's say, we predict satisfaction of democracy with differences in income. So we include income as an x variable in a model for satisfaction of democracy as the y variable. And let's assume that maybe it is the case that our model is very, very good at predicting satisfaction with democracy for people with low incomes, but the higher the incomes are, the worse our model is in predicting our dependent variable satisfaction with democracy. So then the variation of errors would actually increase depending on where we are on the scale of the x variable, so on the income scale in this case. And that's one situation. There are lots of different situations where any situation that where the variation of errors deviates from being more or less the same all over is a situation where you have heteroscedasticity. Yeah, so that's one issue that you can run into. What would happen in that case? Well, the good news is it doesn't really matter for your regression coefficients. So you can still estimate your OLS regression model, and the coefficients that you get will be unbiased, although they may not use the data as efficiently as they could be, but basically your coefficients will be okay. But the problem is really with the standard errors. So if you have a heteroscedasticity, then your standard errors, at least the traditional way of calculating standard errors, so the OLS estimated standard errors, can't really be used to meaningfully test the statistical significance of your effects, or say something about the uncertainty related to your effects. Well, why is that? Well, if you think back all the way to the B lecture of the second week, we discussed how we estimate those standard errors, so what the formula behind that is. And we saw that part of that formula is based on looking at the variation in our errors. So the variance that is basically left unexplained by our regression model. But of course, that assumes that that variation can be captured by a single number, so that it is a constant variation. So that assumes that we can actually think of our distribution of errors to be homoscedastic. Because if it's not, if it's heteroscedastic, that actually means that the uncertainty associated with our regression coefficient actually depends on the value of our x variable itself. So you can't really capture it in a single number, at least not in the way that we would do that for an OLS estimation. So in other words, standard errors become a bit problematic if you want to say something about uncertainty or statistical significance. If you have a situation of heteroscedasticity, that your errors are not constantly distributed over the values of your x variables. Another assumption, the fourth assumption that we need to make, is that these errors are not just constantly distributed over the x variables, but they're also normally distributed. So the assumption of normally distributed errors literally means just that if you think about the distribution of all the errors, that overall that distribution should be normal. So really think about that. Well, what would happen if I would observe all the errors? So for all the cases in the population, I observe the errors. So some cases will have large errors, other cases will have small errors, some cases will have positive errors, some cases will have negative errors, depending on whether their predicted value is larger or smaller than the observed value on a dependent variable. So we could make a data set just containing these errors, and then we could look at the distribution of those errors like we would otherwise do with any other variable, and then that overall distribution should be a normal distribution. So that's another assumption that we need to make, that all these errors taken together should be normally distributed. And also there we have the same issue, that it's not really a problem so much for the coefficients as it is for the standard errors, because the way we use standard errors is based on a certain application of the central limit theorem, which works well if those errors are normally distributed. So if they are not, then again we have a problem that the standard errors might not be a great reflection of the uncertainty in our coefficient, and may not be appropriate to test the significance, statistical significance of our coefficients, of our effects. Having said that, this problem is especially worrying if you have a small data set, because the larger your data set becomes, the less this is an issue, because the less you need to rely on your errors to be normally distributed to get good estimates of the standard errors. So if you have super large data sets, then it's not such a problem if your errors aren't really normally distributed. Because then you can still use the standard errors as you would normally do, because the larger your sample is, the more the less bias you will have in your standard errors, even if the original errors are not normally distributed. So this is especially an issue if you have relatively small data sets. And basically that goes for both these assumptions, assumption 3 of homoscedasticity and assumption 4 of normally distributed errors. Both of them aren't really terrible for the estimates that you get for your coefficients, although with heteroscedasticity there would be other ways of more efficiently using the data that you have. But they pose a problem for your standard errors. Yeah, and so especially if you have super large data sets, then you might not be so worried about the normally distributed errors, although you might still think, well, conceptually it's weird to use one standard error to say something about the uncertainty of your coefficient if the distribution of errors is not homoscedastic, so if it has heteroscedasticity. Yeah, but that's basically these assumptions of homoscedasticity and normally distributed errors. Well, that sounds very abstract. You could also visualize these assumptions as what would that mean. So for a simple linear regression model, let's assume that I have an x variable on my x-axis here and a dependent y variable on my y-axis. And all these individual points are the data points based on which I estimated that regression line that we see here using the OLS method. Then the assumption of normally and homoscedastically distributed errors basically implies that our regression line is running straight over the top of a distribution of errors, and the distribution of errors is normal, indicated here by these little normal distribution curves, and it is always more or less the same. Yeah, so there's always a more or less equal amount of variation around our regression prediction. So it's always the same normal distribution that we are seeing. Yeah, so that's basically homoscedasticity and normally distributed errors taken together basically imply that we are fitting a regression line straight over the top of the normal distribution of errors, and that distribution is also constant and no matter where we are on the x-axis, so that we don't have a situation where maybe here all the errors are quite close to the regression line and then here they are all over the place. So you would get something like a distribution of errors that looks like a megaphone or something like that. Yeah. So it has to be constant and it has to be normal. But again, this is especially an issue if you have small data sets. Some comments that I want to make about heteroscedasticity and non-normally distributed errors just up front, because sooner or later when you do lots of analysis you will be confronted with a situation of having heteroscedasticity or not normally distributed errors. What you will often see is that both of those will tend to appear together. It's not always the case, but often you will see that if your errors are not homoscedastic, that they are also not normally distributed, and conversely that if they're not normally distributed, that they're not all perfectly homoscedastic. So that's something you will often see, that these two assumptions are both problematic in the same situation. And one situation where that is quite likely is if your dependent variable itself is not normally distributed. So you may have learned in previous statistics courses that certain statistical methods require your dependent variable, or the variable that you're analyzing, to be normally distributed. Very strictly speaking, that's actually not correct. What they usually mean is that the error needs to be normally distributed. But of course, there is a direct relationship between the distribution of your variable and the distribution of the errors, because, remember, the error is nothing more than the difference between predicted and observed. So if the observed thing is already not normally distributed, then the errors probably also will not be normally distributed. So it's quite likely that if your dependent variable, for instance, is very skewed in its distribution, so left-leaning or right-leaning, so left-skewed or right-skewed, that you will see that also your errors are not nicely normally distributed, and there's also a chance that you might see some heteroscedasticity, although that also can have different origins. And one of those origins is that there is something wrong with the way you specified your model. Specifying the model basically is how did we set up the model, what variables did we put in the model, and how did we put those variables in. We already saw in the last lecture, for instance, that we can apply something like a polynomial transformation if that is required to represent the effect of our x variable and our y variable. And later in the course we will see that there are other ways of including x variables or other transformations that we can apply, or things like interaction effects and dummy variables. So all of those things are ways of specifying your model. So what do you put into the model, and how do you put it into your model? And one of the reasons it's useful to check for issues with heteroscedasticity and not normally distributed errors, even in a situation where maybe you have a super large data set and aren't terribly worried about it, is because if you see indications that there are issues with heteroscedasticity and not normally distributed errors, then that can point to an issue with the way you specified your model. And you might have to rethink about, is there maybe a different way to set up the model? Do I maybe have a variable in there as a linear effect, which very, very clearly isn't a linear effect, for instance? Then including a nonlinear term for that variable should improve make the distribution of our errors more homoscedastic and more normal, for instance. So that and there are lots of other ways that your model might be misspecified. Some of them, like I said, we'll discuss other ways of setting up the models, like with interaction effects and dummy coding, and also those might be things to consider if you see a problem with heteroscedasticity and not normally distributed errors. So it's always useful to check these things. If you read the book, you will see that there are lots and lots and lots of different ways of checking for heteroscedasticity and not normally distributed errors. Of course, remember, these are assumptions about the errors, so basically something that we cannot directly observe, because the errors refer to the difference between predicted and observed in the population. We only observe the residuals, so the errors that we have based on our sample data. But of course we can take a look at how the residuals are distributed to check whether there might be an issue with these assumptions. Because if our residuals indicate that we might have heteroscedasticity or not normally distributed errors, then that you can take that as evidence that that might really be an issue. So you might think about, how can I fix this issue? There is a SPSS syntax file on Brightspace. I would ask you to walk through yourself sometime, where I'm just doing a practical example of how to check for these things, and maybe also address these things if they are problematic, because this is really hands-on stuff. Like I said, there is lots and lots of different statistics you can take a look at, and lots and lots of different graphs that you can take a look at, and some are more useful than others. But the important thing is that you get the basic idea of what may be wrong, and what may be useful ways of trying to spot that by inspecting your residuals. Of course, you might be able to solve the problem by estimating a better model, improving on the specification of your model, but maybe you won't always be able to do so because you don't know how to, or maybe because you don't have the data to do so. So that's something that can happen. So if you aren't able to specify a better model, there is, let's say, one, I wouldn't call it a trick, but something you can do to make sure that the inferences that you are making based on your sample estimates are at least robust to these potential violations to the assumptions of heteroscedasticity and non-normally distributed errors. Robust meaning, the conclusions you would draw from your regression model, to what extent are they actually can you still let's say to what extent are they being impacted by the fact that you might have heteroscedasticity or non-normally distributed errors. So it's always good if there are ways to checking this robustness of your findings. As a matter of fact, if you go further in research, you will notice that a lot of what we do isn't just we have one regression model that we estimate and represent that and be done with it, but a lot of what we do is actually doing lots and lots and lots of robustness checks and robustness analysis to see whether the inferences that we are making on a specific regression model, whether they are sensitive to problems with the assumptions of those regression models, and if they are sensitive, how so, and then think about how can we maybe fix that. So one thing you can do that's fairly easy to do in SPSS nowadays, so that's the reason I'm showing you this, because there are different ways of checking the robustness of your model estimates against the heteroscedasticity and not normally distributed errors. But there is one way that is implemented in SPSS in a fairly easy way, and it's also a pretty good way of checking whether you have an issue. And that is to use bootstrapped confidence intervals to see whether the conclusions you draw about your hypothesis hold up to assumptions of these violations of homoscedasticity and normally distributed errors. So what is bootstrapping? Well, let's take a step back first. What do we need standard errors for? Because standard errors are the thing that are primarily affected by heteroscedasticity and not normally distributed errors. Well, standard errors tell us what our best guess is as to how the sampling distribution of our regression coefficient is dispersed. Yeah, again, so thinking about our regression coefficient that we estimated based on a sample, well, that's one regression coefficient that we have happened to find in our sample. So if you want to say something about the population, what do? We think about, okay, well, what would the sampling distribution of this regression coefficient look like? So the distribution of all possible regression coefficients we could get from drawing all possible samples of the same size from the population, and in each of those samples re-estimating our regression model. And then, of course, we'll find some regression coefficients that are higher, others will be lower, just depending on who we have happened to include in our sample. And then, of course, by the central limit theorem, we know that the average of all those regression coefficients should be identical to the true population regression coefficient, and all the individual regression coefficients in those different samples will follow a roughly normal distribution around that population regression coefficients, if we have sufficient observations in any case. And then, of course, the further removed from the true population regression coefficient the specific sample regression coefficients will be, the less likely it is that you will find such regression coefficients. Yeah, so if your true regression coefficient is something like 0.5, then it's quite likely that you find something like 0.6 or 0.7 or 0.4 in your sample, but it's quite unlikely that you find something like 100 or a million or minus 99 or something like that. Yeah, so overall we get this bell-shaped symmetric distribution around our population regression coefficient, and the dispersion of that distribution of sample regression coefficients. That's the dispersion and the variation in our sampling distribution, and our standard error tells us exactly how that what the dispersion looks like. So how spread out are these individual regression coefficients, because it is really just an estimate of the standard deviation of that distribution of regression coefficients. So that's what the standard error normally does for us, but of course that's assuming that we can actually assume homoscedasticity and not normally distributed errors. So basically the estimated standard error doesn't really tell the whole story if you have heteroscedasticity and not normally distributed errors, but we can do something else. We can try to replicate our sampling distribution. So rather than estimating it based on an estimate for our standard error, we can also try to really replicate that sampling distribution. And this is based on a trick for which there is statistical theory that tells us that this trick actually works. And the trick is the following. Well, normally we think about our sample as being one specific sample from the population. And we think about, okay, what would happen if we draw all specific samples? Now, what we could also do is we could say, well, let's look at the sample that we happen to have observed, and from that sample, take a smaller subsample. Yeah, so basically, for the moment, just pretending that our sample is actually the population, and then let SPSS draw a smaller subsample of observations for us and estimate the regression model on that smaller subsample. And not once, not twice, but many, 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 many times over. So if you're doing bootstrapping, what you're doing is you're telling SPSS, well, take my sample, take the model that I just estimated on that entire sample, and draw smaller samples from the entire sample. Yeah, so and that SPSS is then just using a random probability sampling, and then it will take smaller subsets of the sample and then estimate the regression model on all of those subsets. And each time we'll get a different value for our coefficient, a different estimate for our coefficient, of course. And SPSS is saving all those different coefficient values in the data set, and then using that to replicate the confidence interval around our regression coefficient. Yeah, so rather than estimating the variability around our regression coefficient using a standard error, we are just going to try to replicate that confidence interval. And the nice thing is, if even if your errors are not homoscedastically and normally distributed, this bootstrapped replication of your sampling distribution will correspond roughly to the true population of sample regression coefficients from the entire population that we don't observe. There are some very mild assumptions that we need to make, but it's not those strong kinds of assumptions like homoscedasticity and not normally distributed errors. And so this is really, really useful, because that means that we can just try to replicate the confidence interval around of our regression coefficient. It's been only a couple of years since I've been able to teach this, because nowadays, well, it's well implemented in SPSS, and computers are quite fast nowadays. So as long as you're not using huge data sets or very complicated models, this actually just takes, seconds to a couple of minutes maybe to do, because of course it is quite computer intensive to do the same regression model over and over and over and over and over again. And SPSS really does this lots and lots and lots and lots of times to try to get really a good reflection of the sampling distribution. When I was still studying, it was unthinkable to let students do that on the typical student computer, because that would have taken days if it would be possible at all. So that's quite nice. So I also included an example of that in the example syntax for model checking. Yeah, and then if you say, well, based on my normal regression estimates, I have a significant effect, but I see that I have some heteroscedasticity or not normally distributed errors and I'm not able to fix them, well, then just redo your analysis and this time get bootstrapped confidence intervals. So for instance, if you're working with an alpha of 0.05, you can get 95% bootstrapped confidence intervals, because that of course means the same thing. And then if you say, well, I had, for instance, a positive significant effect in my original model, then check whether the bootstrap confidence interval also is a set of two positive numbers, so that the lowest number of that confidence interval is larger than 0. So that, in other words, that 0 is not contained within the confidence interval, because if the 0 value is outside of that confidence interval, that also means that you have a statistically significant effect. That also means that you would be rejecting a null hypothesis based on the p-value. Yeah, so for a significant positive effect, if you want to check, well, is that robust, do the bootstrapping, then check the bootstrap confidence intervals and look at the lower of the two confidence interval values, because that is that should then be larger than 0. And if it isn't, you know that your finding is not robust to this violation of the assumption of homoscedasticity or normally distributed errors. And that's, of course, something you should absolutely take into account when you evaluate the hypothesis, and it's something you should also report if you're doing a research report. The other way around, if you have a negative effect that you found to be significant in your original model estimate, but you worry about heteroscedasticity or normally distributed errors, again, re-estimate the model with a bootstrapped confidence interval, and then the higher of the two values should be smaller than 0. So both of the values in your confidence interval should be negative values. So again, if the 0 is outside of the confidence interval, then we can speak of a significant effect. Yeah, so that's a nice way of checking that I would definitely recommend using if you have any kind of doubt about whether heteroscedasticity or not normally distributed errors might be a problem for your estimates. That's one thing. Now let's talk about one of these additional sources of bias, which are, well, as we will see, to some extent already captured by these standard assumptions of additivity, linearity, independent errors, homoscedasticity, and normally distributed errors. And one of those things are outliers, but that's something that, because it has it's kind of its own problem that we often talk about in a separate way. But it is basically also, you can capture this under those 4 standard assumptions. So outliers. What are outliers? Well, let's think about our regression model. Let's say we have a simple linear regression model, and we have an x variable, and we have a y variable, a dependent variable. And let's assume we have a very nicely clear behaved relationship. Like in this case, you see that it's obviously there's a positive effect going on. Yes, you see all these individual data points, and we have fitted a regression line to find the ideal prediction through those individual data points, and this is the regression model that we get. Yeah, great, good. Looks great. Errors seem to be constantly distributed, so we don't see any kind of issue with heteroscedasticity or anything. So cool. Okay, so let's think about, okay, what would happen if I would add one more data point to these observations, and this would be the data point. Yeah, so if you missed it, again, look at the lower right part of the figure. So that's what we start out with, and let's assume we're adding this red data point. Yeah, so we have one additional observation that we're using to estimate our regression model. What would happen to the regression line? Think about this yourself. What would happen to the regression line if we added that one single data point and then would estimate our regression model again? Yes, exactly. So you will see that the regression line is being pushed downwards quite a bit by that one single data point. Is that bad? Well, look at how well this new regression line fits with the majority of the observations that we have. And now you actually see that, oh wow, we started out with a regression line that is really, really good in fitting with our observations. And now we added just this one data point, and all of a sudden, yeah, it really doesn't fit very well anymore with what the true relationship is. Yeah, so in other words, this one single data point is really kind of wreaking havoc on our estimates. Now, another thing you can see from this picture is that even though this outlier is quite disturbing the relationship, by really pushing that regression line down quite a bit, it is also very far removed from the regression line still, because of course the regression line is also based on all these other observations that are over here, right? So most of the information is still coming from these observations, so the regression line will be a little bit biased downward in this case, but it will still, the regression prediction will still be quite far removed from these outliers. So in other words, this is good to know, because that means we can now try to identify cases that might be outliers, because outliers will have a large residual. They will be very different from the regression prediction. Yeah. So that's cool. Now we know that there is something we can do to find these outliers, that is by looking at, or potential outliers, and that is by looking at those cases that have very large residuals. Yeah, because those cases then potentially might be outliers, and then it might make sense to maybe take them out of the data set and redo the analysis. Now there's one problem with that. What is large? So when is the value of a residual large? And the difficult thing about that, well, of course, what value residuals take depend on the scale of your dependent variable, right? If your variable is measured on a scale from 1 to 10, that gives you different values for the residuals than if the scale is from 1 to 100 or from minus 900 to plus 1 million or something like that. Yeah. So the value of the residual itself entirely depends on the scale of your dependent variable. So that is difficult because, okay, what constitutes a large outlier? When is an outlier large enough to, when is the residual large enough to say, well, this might be an outlier? So we have an issue with that, that the scale, that is completely arbitrary depending on the scale of our dependent variable. Now again, stop and think, what would be a good solution to this problem? Stop and think, how would you solve this problem? Maybe some of you thought about this solution. Well, if it's a problem of scales, yeah, that the value of this residual is depending on the scale of our y variable, then let's make the scale comparable. And one way of doing that we already saw earlier in this course is standardization. Yeah, so looking at the difference between each in the residual and the average, divided by the standard deviation of residuals. So re-expressing those residuals as z-scores, as standard scores, because then we know exactly what their distribution is supposed to be like. Yeah, so standardization is a way of making the scale comparable, standardizing the scale. So we can do that, of course, for the residuals in our data set. And then the nice thing is these standardized residuals, so these set values, can be compared to the normal distribution, because our assumption is, remember, that our errors are normally distributed, which also tells you already that these outliers are just a specific case of not normal or not constant homoscedastic error distribution. Yeah, so these standardized residuals, those can be compared to the normal distribution because we re-express them as a standard normal distribution. And we know what the standard normal distribution is supposed to look like because we mathematically have a formula for that can describe the standard normal distribution. So for instance, we know that on the standard normal distribution, 95% of our observations are roughly in the interval of minus 1.96 rounded to positive 1.96. Yeah, that's just mathematically. We can show, well, this is what the 95% coverage is of the normal distribution. Yeah, remember that's where the 95% confidence interval came from in the large sample situation. Yeah, and again, if we assume that our errors are normally distributed, that means that, well, we can use this knowledge because this distribution of residuals, if that's re-expressed as a standard normal distribution, then we may expect that 95% of our residuals that we observe lie within that interval of minus 1.96 and plus 1.96. And conversely, we should see that only around 5% of our residuals, so 5% of the cases for which we measure these with standardized residuals, that only about 5% of those observations are outside of that. So have a standardized residual that's either smaller than minus 1.96, so more negative, or larger than 1.96, so an even larger value than that, positive. And we also know, for instance, what 99% of the standard normal distribution is supposed to cover, and it's supposed to cover the interval of minus, again rounded, minus 2.58 to positive 2.58. Again, this just follows from the formula that describes the standard normal distribution. And this is also again where the these critical values for the 99% confidence interval come from in a large sample setting. Yeah, so again we can check, well, is it really true that 99% of our residuals are within that interval of minus 2.58 to positive 2.58, and conversely that only about 1% of the residuals are smaller than minus 2.58 and larger than or larger than 2.58. And again, using again our knowledge of the standard normal distribution, we can say, well, 99.9% may be expected to lie within the interval of, rounded again, minus 3.29 and positive 3.29, because again, we can show mathematically, well, this is these are the two values which capture 99.9% of the standard normal distribution. So that's quite useful. So that's one thing that you can do to see, well, is the distribution of my standardized residuals, is that roughly normal, and isn't there like a bunch of cases that are that are outside of these intervals? Yeah, so are there maybe many more cases than we would expect on a normal distribution that are outside of those intervals, because then those cases might function as outliers, and you might think about maybe taking them out of the data set and re-estimating your models without them. Now, having said that, there is a couple of comments I want to also give on the practicalities of dealing with outliers, and some things you have to really consider carefully when you're a researcher and you want to do a good job at critically analyzing things. One of those is that don't just take out all the cases where you maybe find a large residual. Consider first whether they are even problematic. So outliers are really only a problem when they are also influential cases. And what do we mean by influential cases? That means that if those cases, if you would take them out and you find very different estimates for your coefficients and or for your standard errors. So outliers are really only influential cases if you would take them out and then re-estimate your model, and then you see that your coefficients and or your standard errors change a lot after excluding the outlier. And that's not always the case. So some cases look like outliers, but really it doesn't matter so much whether they're in your data set when you're estimating the model or not not included when you're estimating the model. And then you can just leave them in because they don't really have a lot of impact anyway. And then it's better to retain the information that you get from those cases. The other thing I would recommend doing, especially but not exclusively if you compiled your own data, is if you see cases that are potential outliers, make sure that those cases, that the variables you are analyzing have been coded correctly. Because one of the most common issues that I see, not just in student papers, but also sometimes with, let's say, publishing scientists, is that they have outliers, and then it turns out that the outliers are something like a variable value was coded incorrectly. So it should have said 10, and accidentally if somebody put 100 or 1000 or -9. Often in survey data sets, special values will be assigned to the missing values or the non-valid values, like -9 or -99 or -999. And then sometimes people forget to recode those as missing values. So then your statistical software just will treat them as normal observations. And then, it can happen that you're estimating a model and hey, you find an outlier, and then it turns out to be a coding error. Yeah, so always be aware of that. If you're doing your own research and you find weird outliers, check whether the values on the variables are coded correctly and that are not some coding errors that are actually to blame for this. And of course, if there are, fix the coding errors and then redo your analysis. So that's one. Another one that, especially for political scientists, it's quite good to be aware of, is that especially if you're doing comparative, so country comparative research, for instance, these outliers that you find, let's assume that they're not based on coding errors, but they're real outliers. They might actually be theoretically interesting, and you will have probably already learned about certain case selection techniques for qualitative case studies in the PSRM1 course that are really based on this idea of we can do a type of regression or statistical model, and then we might find some outliers, and then it might be theoretically super interesting to especially do a case study on those specific outliers. Yeah, so that's something to be aware of. So outliers aren't necessarily always just a problem, but they can also be interesting to further investigate whatever you're trying to investigate. Now, really only take out outliers if they clearly bias your findings. Don't do it just to make your model fit better, because that's a temptation you might have, that you say, well, okay, I'm estimating a regression model and I feel thought really well about my hypothesis and what control variables to include, and super excited to do that, and then you're estimating the models, and then you find that the goodness of fit is terrible or not as good as you would have hoped. So maybe your R square isn't all that impressive, and you think, okay, that's bad. And then you think, okay, let's just take out some of those cases with large residuals. Well, because they may be outliers, but what you will see happening then, of course, is that you re-estimate your model and the model fit will improve because you're taking out the cases that are contributing to a not so good model fit. Yeah, remember, outliers have a large residual. So now you have a model that's better. And the effects that you find might be clearer, stronger, more statistically significant. Great. You might even think, well, let's take out more of these outliers and then re-estimate the model again. And of course, then again, the model fit is going to improve and your estimates of your effects are going to look even more impressive. But of course, all that you are doing in that case is basically looking for the results that you want to find, rather than applying statistics in a way that is critical and that critically addresses the data, because you're basically excluding the data that doesn't fit with your preconceptions. So really only exclude outliers if it's like really clear, okay, this is biasing my finding quite clearly, and it's not just a case of I'm trying to make my model fit better just to make my model fit better. And then I would say, if you do that, it is really a task for you as a researcher to clearly motivate why you are excluding cases. So really think about why might that be an outlier if you can. Especially in country comparative research, if you're doing regression analysis, that is usually the case that you have some story about, okay, but this country is really so different that it doesn't make sense to include them in the same regression model. But be clear about the motivation, and if you do so, if at all possible, present both estimates. So present your regression model with the outliers included and with them excluded. So also the people that read your research can judge for themselves whether this was a good choice to exclude your outlier, and which one of those estimates they trust more. Yeah, of course, at the end of the day, you are the researcher and you need to make those decisions, but it's important that you are clear about how you reach those decisions, and ideally also show, well, how sensitive are my results to those decisions. Yeah, so please be a bit careful with that. So I'm always very much on the conservative side. So unless there is like a real obvious problem with an outlier, I tend to leave that in, because I think, well, yeah, that's just how noisy the data are, and I have to live with that, because otherwise I'm a bit too worried about maybe cheating a little bit too much. Yeah. So try to be an ethical researcher with that, with these kinds of decisions, and be clear and honest about them. Okay, so that was it for basically the standard regression assumptions, and how they are also related to outliers, and how you can spot them and what you can do about them. So let's reflect a little bit on where we are now. Maybe you are right now at the stage where you want to bang your head against the wall in the hope that it will make the statistics go away. Hang in there. It's just a couple of more weeks, and then you will be rid of them for a little bit. At least for this course. But I also want to talk about where are we now in terms of what do we now know about regression models. So what we know is that we have multiple linear regression models, and that we can think about them as describing the observed value on our dependent variable for each case I as given by a constant b0 plus a set of regression coefficients for each x variable that we include in our model, plus an error term that indicates the difference between what we know based on those regression coefficients, so what we know based on the information that's contained in the x variables about the value of the dependent variable, and what we actually observe in the value of the dependent variable, because these are probabilistic models that allow there to be some error, and that error is of course the difference between what we would predict based on the model and what we actually observe in our dependent variable. So the y with the little hat on top, so the y hat value indicating the predicted value, which is only based on the informative part of our regression model. So basically all the regression coefficients multiplied by the values of the x variables plus the constant, but excluding the error term, because of course the error term is the part of the value in our dependent variable that we are not able to explain with our regression model. So that's what we already know. We also saw already that we can interpret a regression model as giving us a conditional expected value of our dependent variable. So the regression model can be thought of as a description of the conditional expectation of our dependent variable. So remember, the E here stands for the expected value, and we're talking about the expected value for our dependent variable conditional on, so the upright bar here means conditional, so depending on the values of the x variables that we have included. And we already talked about that one way of thinking about the expected value, although not entirely mathematically correct, but quite useful, is to think about that as the best guess for a dependent variable for a randomly drawn from a case randomly drawn from the population, and if it's a conditional expected value for a randomly drawn case from the population, given that we know what the values on variables x1 and x2 and all the other x variables in our model are. Another way of thinking about the expected value is it is the value that we would get in the long run. So if we would redo our regression model over and over and over again on all different samples from the population. So the idea is that in the long run, we get the expected value on our dependent variable. So predicted value, that's something we can say about our specific sample that we can calculate for each case based on our specific sample. The expected value really is something about, okay, what would happen if we would do that over and over and over and over and over again. And that would be then the expected value of our dependent variable. And of course we want, if we say, well, we want to have unbiased estimates, that basically means that in the long run, our regression model should converge. So the expected value should converge to the true population value that we are interested in. And that's basically what unbiased means, that we recognize that each specific sample estimate might be a bit wrong, but it is at least unbiased in the statistical sense. If you can say, well, yes, but in the long run, if you would do this over and over and over again with different new samples, then in the long run, these regression coefficients that we find will converge to the true population regression coefficients that we want to say something about. So for unbiased estimation, we need to, as we just saw, make a couple of assumptions that need to be true. So linearity, naivety, independent errors, normally distributed errors, and homoscedastically, so constantly distributed errors. So that's really the role of those assumptions is, well, okay, when do we on average in the long run get to the true population values for our regression coefficients and the associated standard errors, of course, for those regression coefficients, and what needs to be the case. And we saw, okay, then we need to make these couple of assumptions. As a matter of fact, we can summarize all of these assumptions in a very simple formula. So that very simple formula I'm showing you now. I don't think it's in the book, but you will see it a lot probably in your future studies. So it's good that you are already exposed to it now, so you know what it means. And this formula is really, it's a description of what we assume to be true about the distribution of our error term in our regression model. So it's really a summary about, okay, what is it that we assume to be true about this error term that we have in our regression model, because all of the assumptions that we make are basically related to how do we think about the distribution of our error term. So going over that step by step. So these assumptions, as we already mentioned, of course, are really assumptions about the true population errors. So not the residuals that you observe in your sample data, but the true population errors that you would get for all of the observations in the, let's say, true population regression. So we have these true population errors, and then we have this little tilde symbol, which is meaning to indicate that what follows after this symbol is an indication about what we assume to be true of the distribution of this error term. So we have these true population errors, and we assume that they follow a distribution that is, and then what comes after tilde symbol tells us, well, what it is, what that distribution is supposed to be. And then what we get here is the large letter N, indicating that we assume that our true population errors follow a distribution that is normal. So that is the assumption of normally distributed errors. Yeah, that's that. Now we have that in a formula. So we assume that our errors follow a distribution that is normal, and we assume that this normal distribution has a mean value of exactly 0. Now that one is a little bit more complicated to understand, but basically that captures the assumption of linearity and additivity. And I think the best way to think about that without getting all mathematical is thinking about, okay, let's say we have a simple linear regression model, x variable, y variable, and we're estimating that regression model using OLS. So then we then get a regression line. And notice from when we first discussed this that why are we using OLS? Yeah, so minimizing the squared sum of the residuals rather than just minimizing the value, the sum of the residuals, because the residuals perfectly cancel out. Yeah, so the best fitting regression line is that regression line for which the positive and negative regression for the positive and negative residuals exactly give us the sum of 0. Which also means that the mean of our residuals will be 0 because those positives and negatives perfectly cancel out. So in other words, the model that we estimated, by definition, has residuals that have a mean 0 value. So what we say when we say we assume that our true population errors are normally distributed around a mean of 0 is basically saying the assumption that we have estimated, in fact, the correct regression line. So, for instance, if the true population regression should be a curvilinear relationship, then the mean of those errors will not be 0 because assuming that we just estimate a linear regression model in our sample, because then we are not capturing the true relationship. Yeah, because what we have in our sample is the one that makes residuals 0. So if the true population regression is a different data generating process, then the mean value wouldn't work out to 0 anymore. So this is really capturing this assumption of linearity and additivity in a single number, assuming that we have a normally distributed error term with mean 0. If you don't fully get that, also don't worry, it's not terrible. But you will see later on, if you study more statistics in other courses, then this will come back many times, and variations of this are going to come back many times. And so then we have the last part in that formula, this sigma squared. Of course, you hopefully still remember that we always use sigma squared to indicate the population variance. And notice here that we are assuming that there is some variation in our error term. Yeah, so it's normally distributed with a mean of 0 and some amount of variation. We don't know what amount of variation, but there is some amount of variation that can be captured by a single number, because we have one symbol in here to indicate the variance. So in other words, we are assuming that there is a single variation in our errors. In other words, that we have a single variance, and that variance then has to be constant because we only have one value to express it with. So in other words, this captures basically the assumption of homoscedasticity, that the variation of the errors is constant. Yeah, so all of these 4 standard assumptions are basically captured in this formula. The one I did not yet discuss as being captured by this formula is the assumption of independent errors, but that is because also the assumption of independent errors is being captured by this sigma squared term. And why is that? Well, because you could say if you have a situation of serial correlation, autocorrelation, or interclass correlation, which would be a violation of the independent error assumptions, which we discussed in the A lecture, then you can also think about your data set of being composed of multiple sources of variation. Yeah, so for instance, what we talked about when we talked about the European Social Survey, if we would be using all the countries, then we have a data set that's probably going to have some intraclass correlation in our dependent variable, whatever dependent variable we are looking at, because values on that dependent variable will be similar for people from the same country. So that's the intraclass correlation. But that also means we can basically think about 2 sources of variation in our dependent variable, the differences between people and the differences between countries. And the same thing goes for the idea of autocorrelation, is that there's basically 2 types of variation: the long run variation over the entire data set, and the predictability from one period to the next period. So which really means that if we talk about variance in our dependent variable in data sets where the independent error assumption is violated, that basically means that there are multiple sources of variation going on. So we can't treat it as just a simple random sample. And of course, if there are more sources of variation in our dependent variable, that also means that there are more sources than one source of variation in our errors. So again, implying that there isn't a single value for the variance, because there are multiple variances that we should be taking into account. Yeah, so this single sigma squared value here indicates both homoscedasticity as well as the assumption of independent errors, which, by the way, is also the reason why these are sometimes used interchangeably in some statistical literature, because both are basically a problem of variation in the variance of our error terms that we are not capturing with this model. So that's basically a way to really summarize this in a very efficient and neat way. And like I said, it's not terrible if you don't fully understand it now, but in later courses you will see, you will see this come back, and then you can also see how these assumptions can be extended with more complicated models, so that allow you to have these more complicated data structures. Yeah, so that's for the 4 standard assumptions. But then there's still one thing we need to discuss a bit further, because so far we are basically talking about, is the expected value really converging to the true population value? But this is really not yet a story about causality. It only tells us, well, basically, does it in the long run converge to the best guess for a randomly drawn case from the population, given that we know something about different X variables. Yeah, so it's purely predictive in that sense, not necessarily causal, because you might think you could even include variables in your model that are absolutely not causal, but they are just good predictions. Yeah, so then it doesn't really matter in terms of just a conditional expected value, right? I mean, I could say, well, maybe my dependent variable is H, and I'm including something like satisfaction with democracy as an X variable. Obviously, it's quite unlikely that satisfaction with democracy is going to lead to differences in age, but it can be a good predictor maybe of age. So okay, that's fine. So it's still a quite uncausal story we are talking about so far, because all the B coefficients basically tell us, if they're unbiased, is how the expected value changes if X increases by 1 unit on its scale. So when can we now also interpret these changes in the expected value as causal effects of X and Y? In other words, when do our regression coefficients converge not just to the expected value in the conditional expected value, but the conditional expected value of the causal effect in the population? So when is this the case? And for that, the 4 standard assumptions aren't enough to talk about bias in our estimate. We need to go a bit further. Specifically, we need one more assumption that we haven't discussed explicitly yet, although implicitly we have already discussed it. And that assumption is the assumption of exogeneity. So that's again a super fancy Scrabble word. But there, of course, as always, I'm going to tell you what the story behind this assumption of exogeneity actually is. So let's think again about our regression model. I'm going to write it as a model, but I'm also going to show you as a conceptual model with variables and arrows indicating relationships between variables. So we have our regression model, and we have a dependent variable y, satisfaction with democracy, level of democracy, how much you like statistics, whatever your dependent variable is, and you observe that for different cases, and you want to explain differences in that dependent variable. Okay, so we can have a regression model where you can say, well, we have a constant plus b1 x1 plus b2 x2 and so on and so forth, depending on how many x variables you include in your model. And again, representing that in a graph, you will get this kind of conceptual model where I put the independent variables on the left-hand side and the dependent variables on the right-hand side, and we draw arrows from left to right, indicating that our x variables are expected to have an effect on our y variable. Again, not my choice, but it's very confusing that we have different conventions about where to put y and x when we write the statistical model versus as to where we do it if we have a graph, but it's just the way it is. So for graphs, we put the dependent variable on the right-hand side. For models, we put it on the left-hand side. Yeah, but this is just a graphical representation of this regression model. And of course, we don't expect our regression model to be perfect, so we assume that there is some residual error associated with our dependent variable. So all the other stuff that is going on in making the values on our dependent variable what they are, that isn't being captured by these x variables that we included in the model. So I'm drawing an arrow here because that indicates that there's also this kind of, all these things that we cannot observe that go into making the value on y is what it is for the different cases. That's our error term after all. Yeah. So what does it mean when we say we need to assume exogeneity? What we are then saying is we need to assume that our x's, so the variables that we put in the on the right hand side of our model, so the x variables, that those are not correlated with the error term, with the true population error term. Yeah. So there should be no correlation between our error and the values of our x variables. That is what the assumption of exogeneity means. Yeah. So there should be no connection between our error term, no correlation between our error term here and our x variables here. Okay. So again, this is our graphical representation of our regression model. So I think the best way of understanding what exogeneity implies is if we talk about the reverse, endogeneity. So endogeneity is the reverse of exogeneity, and in endogeneity bias is a situation where we say, well, this assumption of exogeneity is violated, is not true. So in other words, if we say there is some correlation between our error term and one or more than one of our x variables, that is what endogeneity bias represents. So we say basically that if we expect endogeneity bias, we expect that there is some kind of correlation going on between our error term over here and one or more than one of our x variables over here. Yeah, so that would be endogeneity bias. And there's a couple of reasons why that may be the case. There's a couple of reasons why we might get endogeneity bias. Yeah, and if we have endogeneity bias, we know that our regression coefficients in our model in the long run do not converge to true causal effects that we want to capture. And the most common sources are omitted variable bias, reverse causation and simultaneity, selection bias, and measurement error. So those are the most common reasons why we might get endogeneity bias, and that meaning that there's the regression coefficients that we find aren't a great representation of the true causal effects. Yeah, omitted variable bias, reverse causation, simultaneity, selection bias, and measurement error. And I'm going to discuss them now with you because that will also hopefully help you better understand why we talk about endogeneity when we say, well, there's a correlation between our error term and our x variables. So let's start with the example of omitted variable bias. So omitted, leaving something out, variables, so leaving out variables, and bias that is related to leaving out variables, that's omitted variable bias. So let's assume that we are interested in getting an estimate of the actual causal effect of some independent variable x on some dependent variable y. So for instance, the causal effect of lecture attendance on the grade in PSRM2, the causal effect of income on satisfaction of democracy, the causal effect of economic development on democratic development. Yeah, so we can represent this as a simple conceptual model. So we have an x variable and we have a y variable, and the arrow runs from left to right, indicating that there is expected to be a causal effect. And of course, we have an error term that indicates all the stuff that makes the value on our dependent variable what it is, that isn't associated with this causal effect of our x variable on our y variable. And now let's go further, and let's assume that there is some third variable z that is a cause of both y and of x. Yeah, you already know these types of variables are referred to as confounding variables. So this potential z variable is a variable that would have an influence on the values on our dependent variable, and it would have an influence on the values of our independent variable. Yeah, so the typical case of a confounding variable. Yeah, so maybe let's see, maybe yeah, I'm using the same example that I used a couple of times already. Let's say I'm interested in the causal effect of income on satisfaction with the government, for instance, and maybe it is actually the case that age is also a reason why people feel differently about the government. So it has a causal effect on satisfaction of government, and age is also a variable that has an effect on income. Yeah, because of course as people get older, they tend to earn more money. Yeah, so z is then this potential confounding variable that is a cause of both our dependent variable as well as our independent variable. Yeah. So what would happen if we would omit a z from our regression model? So not include this z variable in our regression model. Yeah, so we are not controlling or adjusting for differences in z. Okay, let's consider exactly what would happen if that would be the case. Well, one thing to note is that because we are not including z in our regression model, the differences, so the variation in y that is due to differences in z, so that is due to those to the variation in the confounding variable, is now not explained. It's unexplained variation basically in our model because we are not including z in making predictions about our dependent variable. So where does that variation go? Well, that variation then winds up in the error term, right? Because the error term is capturing all the stuff in our dependent variable that we are not able to explain with our model. So in other words, if we are not including a model, a variable in a model, then the variation in the dependent variable that's associated with that variable that we are leaving out is being captured by the error term. So this unexplained variation is in our error term. So now we have a correlation going on between our error term and our z variable. Yeah, so now we have these unexplained differences in our dependent variable that we know are actually differences that are due to the z variable, so they are correlated with the z variable. And if we would assume that z has no effect on x whatsoever, this itself would not be problematic yet. Yeah, because then it's just, well, okay, there's lots and lots of different variables that might have an impact on our dependent variable. We certainly won't ever be able to measure all of them. And it's completely fine because those are probabilistic models. Yeah, so we don't assume that we want to perfectly predict the outcome. So it's fine that there is an error term. So that itself is not problematic. The problem really comes from z not only being of influence on our dependent variable, but z also having an influence on our independent variable. Yeah, this is the reason why in the assignment that you had to do last week, I think, you had to think about confounding variables, and you had to think about, okay, these are supposed to be variables that have potentially an impact on both my dependent as well as on my independent variable. Because only if both of these situations are the case, then you have an issue. Because that means that we know that because z is a cause of x, yeah, z, this third variable, is leading to difference in our x variable, yeah, then of course by definition there will also be a correlation between z and x, because well, z is leading to differences in x. So different values on our h variable, for instance, is leading to different values on our income variable. So now we have, of course, a correlation between z and x. And okay, so what does that mean? It might now means that if we look at our error term is correlated to our z variable, but we didn't include the z variable in our model, and the z variable is also correlated with our x variable. So now we have an indirect path that we haven't modeled between our x variable and our error term. So in other words, through this z variable that we are not including in our model, we now have created a correlation between our error term and our x variable that we did include in our model. In other words, what has happened is we made our x variable endogenous. So where does this term endogenous come from and exogenous? Endogenous basically means this is something that is determined within the system of variables that we are considering, whereas exogenous means, well, this is a variable that is determined outside of the system that we are observing. So in this case, note that our x variable, the value itself, is actually determined indirectly through this correlation with the error term. So there's actually an error pointing towards our x variable that is derived from something that is following our x variable. So it is determined actually within the system. So it's endogenous. And if we go back to what we started out with the idea that our x variables are exogenous, so that they are not determined from anything that is following them. So there's lots of other stuff that might have an impact on the values of our x variables, but there is nothing that is following our x variables that itself again has an impact on our x variables. So that is what exogeneity really refers to. It's the idea that these independent variables that we have, that those are determined outside of the system of variables that we are observing. Of course, our dependent variable by definition is endogenous, because that's how we're setting up the model. We're saying, well, this variable is, the values on this variable is being influenced by these preceding x variables, but the x variables are assumed to be exogenous. So for instance, if you're looking back at this as assumption of the effect of income satisfaction with government, to assume that the income is exogenous is basically to say, well, there's lots of stuff that might have an influence on income. Of course there is, but none of the stuff that is following in my conceptual model after income is having an effect on income, on the values of income that we observe. Yeah, that means that we can treat these x variables as exogenous, and if that's not the case, then we get a correlation between our error term and our x variable. That means now our x variable is endogenous. So we are suffering from endogeneity bias. If we would use a bit less technical terminology, we would say, well, what's the problem here? The problem is that there are differences in our dependent variable that are associated with the differences in our x variables, not because of the causal effect of our x variable, but because the relationship between our x variable and our dependent variable and the z variable that we are not including in the model. So due to this confounding variable that we did not include in our model. Yeah, so again, coming back to the example of income and satisfaction with democracy, if let's say it is indeed the case that age has a causal effect on both satisfaction with democracy as well as on income, and we haven't included age as a control variable in our model, then differences in satisfaction with democracy that we now find to be associated with differences in income, yeah, so they are captured by a regression coefficient, aren't due to the causal effect of income, but they are really due to differences in age that we are not modeling, that we are not including in our model. So that's endogeneity bias. And that means that whenever you have that situation, that your regression coefficient for that x variable will be a based on, let's say, the non-causal overlap of our x and y variables, so the non-causal part of our xy covariance. Remember, regression coefficients, if you look at what the mathematics behind that, those actually do, it's basically looking at what are the unique bits of covariance between our independent variable and our dependent variable. So we're using that covariance to get the value for our regression coefficient. And if we have endogeneity bias, that means that we are basing our regression coefficient on a covariance that's not entirely due to causal effects, so a non-causal covariance. Of course, it might be fully non-causal in the sense that we have a situation of complete spuriousness. So that would be the situation if all the differences in satisfaction with democracy that we attributed to income are actually entirely due to differences in age. So there is no income effect at all in reality. But quite often you will see that it is partial, that there might still be some causal effect of our x variable. But there might also be some endogeneity bias because there are these confounding variables that partially also create a covariation between x and y, and we are not including in the model. That means that at least part of that covariation is not based on the causal effect of our x variable, so that can then partially bias our estimate of the causal effect of our x variable. So that's a way of thinking about the assumptions that we need to make to actually speak about causal effects. We need to assume endogeneity. And of course, one thing is, we can't test that because we can only observe the variables that we do have, and we can only observe them for the sample that we do have. But of course, we can think critically about our model and our design and the data that we have, and think about, did we include all the relevant confounding variables? And if you go further in statistics, you'll see that there's another couple of neat little tricks that you can do to maybe decrease the problem of endogeneity. But I can also tell you that there is no magic bullet, and there is no single way that would ever allow you to completely prove that you are not suffering from endogeneity bias. So this is always, at the end of the day, based on assumptions that are ultimately not provable. There are different ways to analyze whether or not something is or isn't causal. There is a different type of language that's being developed, very much driven by philosophical developments also behind what we mean when we talk about causality. That's something that I'm not going to go into in these lectures, because I think this is already quite more than enough for you. But of course, as always, if you're really interested into getting into these new development in the language of statistics and how they are tied with philosophical developments around what do we mean when we talk about causality, then of course ask me in one of the Zoom sessions. As always, I'm quite happy to talk about these things at length. Too long sometimes. But that's basically the idea of omitted variable bias as a source of endogeneity. Well, how does that work? Well, because we are leaving out a variable that we should be including a potential confounding variable, we get a correlation between our error term and our x variables. So you now might think, okay, as long as I include then all relevant confounders, I will get an unbiased estimate of the causal effect, right? And of course, my job is to disappoint you all over and over again. No, even if you have included all the relevant confounding variables, you still might have an issue with endogeneity bias, because there are also other reasons why you might get endogeneity bias. For one, there might be a situation of either reverse causation or simultaneity. And this is quite simply explained, the idea that you might think that X has an effect on Y, but it might actually be the other way around. So that is the issue reverse causation. So think about a model where we are using differences in satisfaction with the government to explain differences in age. Nothing is stopping you, SPSS certainly isn't stopping you from using age as a dependent variable and satisfaction with democracy as an independent variable. And the statistics still work. You can still get an estimate for that regression coefficient, because you can still have a covariance between age and satisfaction with democracy. So nothing is stopping you from doing that. But of course, if you think about it theoretically, it seems quite implausible that it is really the case that it is difference in satisfaction with democracy that are leading to difference in age. It's much more plausible that it's working the other way around, that difference in age are leading to differences in satisfaction with democracy or satisfaction with the government. So that's what we mean with reverse causation, is that the dependent variable and the independent variable that you identified in reality actually work the other way around. And a related issue is the issue of simultaneity, where it's a little bit of both. So there is, to some extent, X is a cause of Y, but to some extent it's also the other way around, that Y is also a cause of X. And if you want to have a beautiful example of a research field where this is an incredibly difficult problem to solve, is if you talk about studies on democratization and how democratization is related to economic development. Because yes, there are theories that say more economic development leads to more democracy. But then there are, of course, also theories that say, yes, but more democratic countries tend to do better economically. So if we are just comparing countries and doing regression models or any kind of other analysis, including all types of qualitative analysis and case study research, where we're just looking at one moment in time as how is the what is the regression effect, for instance, of economic development on the level of democracy? Yes, we're assuming that it is only one, the causality is only running from economic development to democracy, but it's quite plausible that it's also running the other way around. So they are simultaneous in the sense that they are both causes of each other. So that's a quite difficult issue to solve often, because even with lots of data and even with longitudinal data, it is statistically still very, very hard to, sometimes impossible, to tease out the XY and YX effects from each other. So that's something to always be aware of. Does it make sense to use my X variable as an X variable and my Y variable as a Y variable? Another thing that is causing endogeneity bias is so-called selection bias. And the best way of thinking about that, although again, I'm going here over, I'm kind of brushing over many of the complexities, because that would be a whole course on itself, but just so you get a basic understanding, is to think about the probability of observing values on your dependent variable and your independent variable. Yeah, just think about that itself as a variable. Right, so you could say, well, there is this variable. I don't know what the variable looks like. I can't actually see the variable. I can't actually measure the variable. In statistical terms, we would call that a latent variable. So it is something that can vary across our cases, but we can't actually directly observe that variable. But we can think about just this kind of latent variable that indicates probability of observing our values on our variables for the different cases. Well, once we think about that as a variable, we can just think about that like any other variable. We can think about, well, is that variable measuring the probability? Is it likely that this is associated with what we with the observed values on Y for the remaining cases? And is it likely that it's observed that it's associated with the observed value for X variables for the cases that we do observe? Because if that is in fact the case, then basically that variable measuring the probability of observing these values should be included as a control variable in your model. But of course, usually you can't because you can't observe it. So you get basically a specific situation of omitted variable bias, which we then call selection bias. Yeah, selection because there is a selectivity in your sample. It is not random. The observations on our variables are not a random draw from the population where each case has an equal probability of being included. Yeah, so we have missing information, missing cases, missing values on our variable. So the best way to think about that always is just think about it like omitted variable bias, but then relating specifically to a variable that would measure the probability of having observations on our variables. Yeah, so that would be selection bias. And the last major issue where you will see endogeneity bias occurring is due to measurement error, which really comes back to, yeah, well, basically the first methods courses that you probably did, where you probably heard a lot about, well, if you want to measure things in variables, you need to think about reliability and validity. So do the variables actually measure the things that you want them to measure? That's validity. And they do so in a way that's actually reliable in the sense that if we would add more observations of the same measurement, that we would also really get the same values on our measurement. Yeah, so in other words, if you have problems with reliability and or validity, that means that there is a difference between the observed values on your variables and the true values that you actually want to measure on your variables. And this too can lead to a situation of endogeneity bias, which can go in various different directions. If it's completely random, your measurement error, so it's not that there's any kind of pattern to it, but it's basically just completely random. We're talking about a simple linear regression model. Then what will happen is that the value of your coefficients will tend to be lower, so closer to zero. So positive coefficients will be a smaller positive number, negative coefficients will be a smaller negative number if you have measurement error on your x variables. This is sometimes called attenuation bias, but that's only in a simple situation of a simple linear regression model with random measurement error. Of course, measurement error might also be systematic, and then it's really hard often to predict the direction of the bias, so whether your coefficients are an over or underestimation of the true causal effect. That can go different ways, but basically also think always about, well, are my variables reliably and validly measuring what they are supposed to measure theoretically as the causal variables of interest. Yeah, so I'm going over these things quite quickly because, again, it's a second year course. There is a limit to how far I can and should go with these things, but it's good that you already are aware of these issues and are aware of these different causes of endogeneity bias in a concrete setting. And of course, as always, if you want to know more, please come to the lab sessions. They are lots of fun, and the more the merrier, and ask me. That's what I'm here for. Yeah. So to close off on this, when the first lecture of the first week, in the introductory lecture, I showed you this graph. And I told you, well, this graph, where we have the predicted grade on the PSRM2 on the y-axis, and we have the percentage of lectures attended on the x-axis, and then I drew two different lines, the blue line for students that did not complete all the assignments, and the red line for the students that did include all the assignments. Yeah, and I told you, well, I didn't make this up. This is based on actual data of students that previously took the PSRM2 course, because I measured their grade, of course. I also kept track of lecture attendance. So I used to let these lists go around where people had to put down their name to sign off that they were in fact in the lecture. Never mandatory lectures, of course, but then at least people could sign off if they were there. And then in the past, we used to have a situation where you were excluded from the first exam if you did not complete sufficient assignments, but then we still had the situation where people could be included in the first exam if they had 6 of the 7. But of course, ideally they would have done 7 of the 7 assignments. So I had basically 2 sets of students that actually did the exam, those that did not complete all the assignments. So those are the students that only did 6 of the assignments, and those that did all of the assignments, so did completed all the assignments, because of the remaining students, of course, weren't even in the exam. This changed nowadays. You can't pass the course anymore without having 6 out of the 7 assignments completed. But that was what I was able to measure. And of course, predicted grade is something that you only get for those students that are actually in the exam. And I used the regression model, so I used the predicted grade, and I used the percentage of lectures attended as an X variable. And I included a second variable, so did complete all the assignments, did not complete all the assignments. That was actually a categorical variable, which we'll discuss later in this course, how I did do that. So how did I make sure that there is this second, these 2 lines that distinguish between the students that did and did not include all the assignments. But you can think about this as a multiple linear regression model with 2 X variables: lecture attendance and whether or not people completed all the assignments. Now, the big question is, does this upward sloping line, so this positive regression coefficient that we find for attending lectures, does this represent a causal effect? Of course, I would quite like to say, well, obviously it does, because of course this must reflect just how good of a teacher I am. So this must be a causal effect of me being me. Yeah, absolutely. No questions asked, of course. I imagine you might think differently about that, and some of you might think very differently about that. That's great. Tell me why. So think about this for yourself. Can I interpret this effect of lecture attendance that I'm estimated here in this regression model? Can I interpret this in a causal effect? And of course, I can already tell you, probably not. And I can think about of at least 10 to 15 reasons why this obviously may not be the case. But I'm not going to tell you what those reasons are. I want you to think about this. So what are the reasons why this might not be a good representation of the causal effect of lecture attendance? So in other words, think about where might endogeneity bias come from. So think about the omitted variable bias. What are things that I should have included in my model that I did not include in the model that may have induced now a correlation between the error term and the X variable of lecture attendance? But you can also think maybe even a little bit further. Think also about might there be an issue with, for instance, selection bias? Might there be an issue with reverse causality or simultaneity? Might there be an issue with measurement error? So what are the reasons why this might, these estimates might suffer from endogeneity bias? Think about this for yourself, challenge yourself. And if you have good ideas, let me know in the Zoom Friday afternoon sessions if you want to discuss, well, is this a reason for endogeneity bias? If you want to think about this. And of course, also do that so you can tell me why my teaching isn't causally all that good, actually, because that's, of course, also fun. Yeah, I'm really looking forward to hear about your thoughts about this one. For now, this was it for me. I'll be seeing you on Friday. Bye bye, ciao ciao, and take care of yourself.